The exemplar-based face sketch synthesis framework typically involves a training photo sketch dataset. The photos and sketches are well aligned. The testing photo is divided into local patches. For each patch, a k-nearest neighbor search is performed between testing and training photos. The similarity measurement is based on pixel luminance difference. After KNN search, candidate photo sketch pairs can be identified. After selecting candidate photo sketch patches, existing methods either involve the Markov random field or sketch denoising scheme to combine sketch patches into output result. The quality of the synthesized sketch hinges on whether correct candidate patches can be obtained through KNN search step. For ideal case where both testing and training photos are captured in frontal view, normal lighting and neutral expression, pixel luminance-based distance metrics enable correctly matched patches to synthesize high-quality sketches. However, in practice, when testing photo is captured in different lighting or poses, original metrics cannot find correctly matched patches, which lead to blurry and artifact on the synthesized sketches. Meanwhile, the luminance invariant patch distance like normalized cross-correlation will fail when local contrast within the patch changes due to varying lighting conditions. Inspired by the previous achievements, we in this paper propose an algorithm to remap testing and training photos into similar condition. It enables correct KNN search and existing methods will become robust. To overcome the varying lighting condition, we jointly adapt both testing and training photos to ensure they contain similar foreground and background lighting. For some cases where testing photos are in varying poses or expressions, we pre-warp them into frontal view and normal A expression using local affine transformation. The proposed algorithm can be directly integrated into existing methods with ignorable computational cost. Our algorithm first involves landmarks to detect facial components and use predefined non-overlapping triangles to cover the testing photo. Then local affine remapping is performed to correct testing photo into frontal view and neutral expression, which is similar to the training photos. Then we detect whether side lighting exists through measuring the intensity difference between left part and right part of face region. If side lighting exists, we use adaptive histogram equalization to reduce its effect. Notice that cast shadows still exist around facial component. We try to further reduce its effect using facial symmetric information. For each pixel in the shadow region, we perform a KNN search around its symmetric position using illumination invariant patch distance. After KNN search, we can identify the best matched patch and use it to adjust the lighting of current pixel. We perform this operation densely and relight the shadow around facial component. After side lighting reduction, we adjust both testing and training photos through proposed bidirectional luminance remapping. The remapping algorithm is performed in two steps. First, we globally linear remap testing photo according to the foreground intensity of both testing and training photos. The foreground is approximated using predefined facial region according to landmarks. Second, we adjust the background luminance of each training photo to make the overall statistics of training photos consistent with adapted testing photo in the first step. The background can be pre-computed using offline alpha matte. Then we combine foreground, alpha matte and transformed background into new training photos. Together with adapted testing photo, the new training photos will be provided to state-of-the-art methods for sketch synthesis. The advantage of the proposed algorithm is that it does not require online segmentation or matting for testing photos and thus is efficient and robust. After obtaining the synthesized sketches, we map it back using local affine remapping to yield the final sketch result.